Hello, everyone. Nice to have you back. We're in 815 looking at just examples, more examples of practicing revolution. So recall what we've done is we have two types of calculating solids of revolution, and that is, we're talking about volume, by the way, not area of the curve. So volume, so the first one, which is the more general case. So the general case, which works for all, is your cylindrical washers, which would look like that, of course, with some depth there to it. And that is going to be your volume of pi times your outer radius squared minus your inner radius squared dx, assuming you're going from left to right. Of course, if you're going with respect to y, then it would be from down to up. So again, that's left to right, down to up, whatever that is, of pi outer radius squared minus r squared dy, where then it'd be in terms of y if you're filling washers up in a, well, actually, going with respect to x, if you rotate about the x-axis, you'd have washers that look like this. And going about the y-axis, your washers would look like this. And I like to draw that area of a curve first. Okay, so that's your washers. And then more specifically, and I say more specifically because in the last video I talked about how this is just the case when the inner radius is 0, is we can have cylindrical discs, which is really just your cylinder with no hole, or think about it as your inner radius of 0. And what that ends up just becoming is volume equals pi, and I'll stick with the big R, pi r squared dx. And you can see that's the same thing, but again, your inner radius is 0, where pi r squared dx comes from the formula of a cylinder, which is pi r squared h. Okay. So, or again, so dx, if you rotate around the x-axis, you have your rectangle, you rotate, you would end up getting these vertical cylinders, or discs that, I guess you could say, are vertical. And then as opposed, if you rotate about the y-axis, you'd end up getting your disc to be more flattened out. Oh, why did I make that a washer? Oops. Shade that in as if it's all colored in, because that should be a disc, not a washer. And then that would be pi outer radius squared dy. Okay. So, and then in the last video, do note that just be careful when talking about your radius, because if, for example, say you had some bounded region, I don't know what the bounded region looks like here. Say this is your bounded region, but we're rotating about, say, the line x equals 1 here. All right. Well, in that case, as we rotate around, if you were to draw a rectangle and rotate around, it's technically the backside that we don't see. What ends up happening, and I just want to make sure we're clear, is if I redraw this out here, your washer, where the thickness of that washer is going to be, say, dy, because again, we're filling up rectangles vertically in this space. But the idea there is your outer radius, your big R, all the way to the middle of that circle. So see if I can draw this a little bit better. So if you had a rectangle and you're going from your outer radius all the way to the middle, well, notice that the distance from your outer radius to the curved y-axis, well, that's usually your function f of x. But then since the radius is 1 farther, we have to add that on. So your outer radius, your big R, is typically your function, which I guess would be in terms of y here, f of y, and then plus 1. And your inner radius, in a similar sentiment, is if you have your rectangle, the distance from your inner radius to the y-axis is typically, call it g of y, because it's typically might be a different function. But then we have to add one on. So maybe I call that g of y plus 1. And I don't know if you follow that yet, and we'll do more examples in this video following that, but that is a recap of what we've been doing in last video. So let's look at some examples here. So let's create a bounded region. And I'm just going to create this on the fly, and hopefully it works well for us. So bounded region. And here's some graph. And let's do y equals e to the x. So e, and at 1, it's 2.7, like that. So let's do y equals e to the x, and then we'll go from, we'll also add x equals 1, and x equals 2, and y equals 0. So what I'm doing is we're going to look at the region. There's x equals 1. Here's x equals 2. So these two regions, and then rather than y equals 0, let's do y equals 1. So y equals 1 would be here. So the region we're looking at is this region right here, if I draw that lightly. Okay. So let's do a first one, and let's rotate about, and we'll just say the last video is x-axis. Let's say we rotate about the y-axis here. Okay. Well, no, because I chose e to the x. Let's try to keep it simple. Let's rotate about the x-axis. Okay. So if we rotate about the x-axis, here's your x-axis. Let's use my color. So we look at an area of a rectangle, and I drew one left endpoint. And we rotate about the x-axis. What you end up creating here, rotate about the x-axis would look something like this. And of course, there will be some depth to it. So rotating about the y-axis, we draw our cylinder out. We're going to have washers that look something like this. Okay. So we look at these washers. Well, let's see. What's the outer radius there? Your outer radius is the distance from the outside of our rectangle to the middle of this curve, which is 0. So your outer radius here is just e to the x. So your outer radius is from here all the way to there, which is just, well, yeah, e to the x. And your inner radius is from the bottom of the curve, which is 1. So inner radius is from the bottom of the curve to what we're rotating around, which is 0. So our inner radius there is 1. So our inner radius there, r equals 1. Okay. So using our formula there, we can say then, and the thickness, by the way, will be dx as we fill up more and more cylinders in that space along the x-axis. All right. So our volume is going to be from 1 to 2 of pi times outer radius squared minus your inner radius squared dx here. I'm going to pull the pi out and say 1 to 2 of outer radius squared, which was e to the x, and all of that squared, minus your inner radius squared, which is 1 squared. Okay, and we'll just do this by hand. I don't think it should be too bad. We'll get pi, the integral from 1 to 2 of e to the 2x minus 1 dx. And the antiderivative of that, well, the derivative of e to the x is itself, but because a chain rule would create a times 2, so I just have to count for that. So it's going to be an e to the 2x over 2. Okay, and again, to check that, notice that the derivative of e to the 2x over 2, or think about it as 1/2 e to the 2x, the derivative of this, well, the 1/2 you can pull out in front, and derivative of e to the x should be e to the 2x, the function itself, but because of chain rule, the derivative of the outside leaving the inside alone times the derivative of the inside would be times 2. And now 1/2 and 2 would go to 1, leaving us with e to the 2x. Good. And the antiderivative of 1 would be minus x. And then we're going from 1 to 2. plugging that all in here, we'll get pi times e to the 1/2 e to the 4th minus 2. And then all of that will be minus 1/2 e squared, minus 1/2 e squared minus 1. And doing the best I can simplifying there, you get pi 1/2 e to the 4th minus 1/2 e squared. I'd make that plus 1, so negative 2 plus 1 would be minus 1. And then I'll just leave it as that in this case. There you go. So there's one example there. Okay. Let's do another one. Let's say B. Let's rotate, say, about y equals 1. Okay. So if we rotate about y equals 1, so let's draw a new picture to help you see this. A little sketch. So you have e to the x, you have 1, and then we're going from 1 to 2, so it's this region here. And we're going to rotate about this line y equals 1. Okay. So if we visualize this, like a rectangle that fills up the area between those curves, and we rotate about it, what you end up getting here is a disk with no hole in it. Okay, so let's draw this out. So we end up getting a disk. Okay. So this is a disk. The last one was a washer. And the radius of this disk, use big R here, radius would be from the top of this down to where it's rotating about, which is just the curve itself. So if you notice, if you draw a rectangle, that height of that square is at any moment is provided by e to the x. So that's your radius at any given moment there. And your inner radius, again, if you were using a washer inner, so it would be 0. But we don't need that here if it's a disk. So then it's going to be volume equals from 1 to 2. And the thickness of these is dx. Okay. Volume is 1 to 2 of pi r squared h. That's just your volume of a cylinder. Plugging in what we know here, would be 1 to 2 of pi e to the 2x and dx. Simplifying some of this, we'll get pi 1 to 2 e to the 2x dx, which ends up creating pi times 1/2 e to the 2x from 1 to 2, which gives us our answer here of pi times, let's see here, 1/2 e to the 4th minus 1/2. Well, I'm going to pull out the 1/2. Let's do this. Let's write it as pi over 2 times e to the 4 minus e to the 2. And that's it. There you go. Upper minus lower. I don't know why in my head I was thinking there was going to be more to it, but it's a little bit simpler here. And units cubed. And there's our answer for that one. Good. Okay. So we have a disk, we have a washer, and then let's do maybe one more in this video. I'll recreate it, but yeah, I'll turn it over. That space. Okay. And then C, I'll make the same bound. So there's y equals e to the x, x equals 1, x equals 2, and y equals 1. And this time, let's rotate about y equals negative 2. Okay, let's rotate about that curve. Okay. Let's draw a picture. So e to the x, just go draw this part of the curve from 1 to 2 by the curve y equals 1. So there's your region there. And now we're going to rotate about the line y equals negative 2. So 1, 2 right here. Okay, so we want to rotate about this line here. Okay. So let's see what happens here. We draw this out. area between curve, and we're going to rotate all of these rectangles about this curve here. So what we end up getting is something that looks like so. That you can't see. Technically, that's behind. And of course, it has a depth here, like so. So if I draw this out, well, we can just use this picture here. So what's our outer radius squared? Our outer radius, well, notice it's the distance from the top all the way down to -2. Well, we know that the distance from the curve down to 1, so the distance from the curve down to here, that distance is just the function e to the x. Now, to account for that, how much do we still have to go? Well, from the outer curve all the way down to here, which is your center, right? Or your line of rotation, is we still have to account for 1 and another -2. So we have to account for another +3. So what's your outer radius here? Your outer radius is going to be e to the x plus 3 to account for the distance from out here all the way down to -2. Now, what's our inner radius? Our inner radius is from this part of the circle down to the middle. Let me draw it out here. So here's your inner radius. Well, we know that the distance from the top to here is 1, and then the distance from here down to there is 2. So altogether, our inner radius is 3 there. And that will help us calculate the volume of this washer. So then what we end up getting here is the volume is going to equal from 1 to 2 of pi times outer radius squared minus inner radius squared. And the thickness of this is dx. Okay. That's a very small change in x that we're filling these washers up with. Filling that all in, we have volume is 1 to 2, put the pi out in front. Your outer radius squared is e to the x plus 3 squared minus your inner radius squared, which was 3, and all of that with respect to x, those small changes. And then we'll just put this in a calculator for purposes of saving time. And what we end up getting here is math. And if you wanted to do it by hand, you could. I would probably, if I was doing this by hand, multiply this out, multiply that, combine like terms, and just not have any squared terms, and then find the antiderivative of each term that's separated by that plus or minus. And that could work by hand, but I'm just going to do it in this calculator to save time. So pi times from 1 to 2 of your outer radius squared, which is e to the x plus 3 squared, minus your inner radius squared, which is 3 squared with respect to x. And what we end up getting there is the volume is going to be 162.198 approximately units cubed. And there you go. So a little bit more examples, talking about discs and washers and accounting for that radius change and making sure you can visualize that. Okay, definitely have to do it yourself. It's a lot different when you have to draw the picture yourself, draw out your cylindrical discs or washers, labeling the radius, the thickness, and so forth. All right, if you have questions, be sure to let me know. All right, bye-bye.